In our previous discussion of acids and bases, we have taken a look at the Arrhenius acid-base definition as well as the Bronsted-Lowry acid-base definition. We're going to take a look at one more definition, which is our Lewis acid-base definition. With each of these definitions, they are broadening to include things that have these behaviors but may not have fit into our other categories. So Lewis acids and bases, this is our final definition. And it's just looking at the definition from a different angle. So rather than looking at what happens to the hydrogen, so remember Bronsted-Lowry, we looked at gaining or losing hydrogens. If we're gaining or losing hydrogens, we're breaking bonds. And anytime we're dealing with breaking or forming bonds, we're dealing with electrons. So the Lewis acid-base definition looks at it from the perspective of what's going on with the electrons. According to the Lewis definition, bases are electron pair donors. Acids are going to be electron pair acceptors. So this broadens the acid definition to include cations and molecules with vacant valence orbitals. So this can include metal cations, halides of group 3A, and nonmetal oxides. So having that vacant valence orbital gives us room to be able to accept electrons. Now, so that's the only thing that broadens is to include some things like our metal cations, halides, and nonmetal oxides to be acids. All Bronsted-Lowry bases are also Lewis bases. This Lewis base theory is going to explain why something like ammonia can accept hydrogens. So if we take a look at our ammonia, we have our Lewis dot structure drawn. My nitrogen is considered to be electron rich. It's got these polar bonds and it's got a lone pair of electrons. So we've got a lot of negative charge concentrated around that nitrogen, making it electron rich. Hydrogen, and same is true for our oxygen. The lone pairs in the polar bonds are going to make those electron rich. The hydrogens, though, are going to be considered to be electron poor because they're very strongly electronegative. Oxygen, in the case of water, is pulling the electrons away from the hydrogen. So if the electrons are being pulled away from that hydrogen is going to try to seek out more electrons. It wants to fill up its valence shell, so it needs 2 more electrons. And if it comes into contact with that very electron-rich nitrogen, we're going to be able to get a bond forming. What happens is my nitrogen here, it donates this pair of electrons to this hydrogen. It's going to form a bond with the hydrogen. Notice our arrow here. We've got this arrow, and usually they're represented with half arrows. The drawing program didn't have that, but we have this half arrow. That's representing electrons flowing into something. So as electrons flow into this hydrogen, that hydrogen only has room for 2 electrons. So it's going to break the bond here. So here we're looking at the bond forming between nitrogen and hydrogen. And here we're looking at the bond breaking between hydrogen and oxygen. So as we form that bond with hydrogen, we're going to get our NH4+. As the water breaks its bond to the hydrogen, we're going to get our OH-. My nitrogen here is an electron pair donor. So it is a Lewis base. It's a Bronsted-Lowry base because it accepts a hydrogen. Now, the reason it's able to accept that hydrogen, it's able to form the bond to the hydrogen, is because it has the lone pair of electrons that it can donate to the hydrogen. Now, my reaction is reversible. So to go in the reverse direction, we now have this O-, which has got all kinds of electrons piled up on it. That hydroxide can donate its pair of electrons to the hydrogen. As it does so, that bond to hydrogen breaks, so the lone pair goes back to the nitrogen. We get our NH3 back. The hydrogen goes to the hydroxide. We get our water back. So in this case, the hydroxide is the electron pair donor. So it is the Lewis base. Now, as we said with our Lewis acid-base definition, this was going to broaden our acid scope. And so in the case of metal ions, remember that when metals form cations, this is done through the loss of valence electrons. When we lose those valence electrons, that leaves a vacant valence shell that can accept a pair of electrons. So if you look at an example, we can look at the formation of a complex ion. So most ions you guys have been used to dealing with before have been a simple ion, like an Fe3+. So it's just the iron has lost its electrons. A complex ion is a combination of ions that is still an ion. So not all ion combinations are going to lead to a neutral compound. So in this case, we've got the Fe3+ interacting with this SCN-. So the Fe3+, it's lost its valence electrons. It's going to be a Lewis acid. It's got a vacant valence shell that can accept. My SCN-, if we were to draw out its dot structure, there's all kinds of lone pairs. So that SCN- is a Lewis base. That negative very often means you've got extra lone pairs that can be donated to form bonds. So what happens is we're going to have electrons flow in here to our iron. We're going to form a bond with that iron. Since we're forming that bond, we're sharing those electrons, we're going to get that complex ion, that FeSCN2+. So that iron is a Lewis acid. It's accepting electrons to form a bond. Now, our next example of additional acids are going to be halides of group 3A. And so an example we can look at is boron trifluoride. Now, we got to look back at some bonding theory. So I can draw my dot structure of boron trifluoride. I have boron in the center with my fluorines around it. Each boron-fluorine bond is the same, giving us a coordination number of 3, and we get a trigonal planar geometry. Now, according to our bonding theories, a coordination number of 3 requires 3 unpaired electrons in orbitals of equal energy. So each of those bonds is formed by an unpaired electron from each atom combining up. And to get those equal length bonds, we've got to have equal energy orbitals. Now, if I look at boron's electron configuration, it's helium, 2s2, 2p1. Here it has only one unpaired electron. So we can see that in its energy diagram, where I've got just that one unpaired electron. From that configuration, that would mean that we can only form one bond. But we know boron trifluoride exists. We know it has 3 equal bonds, so something has to happen. So that means that my atom has to undergo excitation and hybridization. If we remember from our hybrid orbital theories, to get a coordination number of 3, this is going to require sp2 hybridization. So sp2 means our s orbital is going to combine or blend or hybridize with 3 of the p orbitals. That gives us these 3 hybrid orbitals. We fill our electrons into those 3 hybrid orbitals. So I have 3 electrons in equal orbitals. That's going to give us our trigonal planar geometry. We are then left with this vacant valence orbital. That vacant valence orbital can accept a pair of electrons. So we have to have a completely empty orbital to accept a pair of electrons. So because boron has that vacant p orbital, when it forms this structure of BF3, that BF3 can be a Lewis acid. If it interacts with something like ammonia, the ammonia has the lone pair. That lone pair can flow into the boron. It can occupy that vacant p orbital and form a bond. And so we can get this bond between the boron and the nitrogen. The NH3 is the Lewis base. It's donating the electrons to form the bond. The boron is accepting it in that vacant p orbital. And then finally, our definition broadened to include nonmetal oxides. in these scenarios, we must have at least one pi bond. Remember that pi bonds are found in double or triple bonds. So an example we can look at is carbon dioxide. That's a non-metal oxide. When carbon dioxide interacts with hydroxide, what can happen is my hydroxide is a Lewis base. It's got all those lone pairs it can donate. So the electrons can flow in to the carbon. Now, that carbon would have to break one of its pi bonds. If it breaks one of those pi bonds, the pair of electrons can go to an oxygen, and that bond breaks. That leaves a vacant p orbital that forms that pi bond. It leaves that vacant p orbital that can accept those electrons. So the electrons come into the carbon accepts it, forming this bond here. The electrons that were part of the original pi bond become here. So those electrons go there. It empties the p orbital that forms the pi bond. That empty p orbital can bond with the hydroxide, forming our HCO3 minus. So because the carbon is accepting the electron pairs, it is a Lewis acid. So we've got three definitions, and when we're defining acids and bases, we've got to keep all three definitions in mind. So with problem 16, with all three definitions in mind, when identifying a substance as a base, what are some things we can look for? So remember our Arrhenius definition, we produced hydroxide in solution. So typically, we can produce hydroxide in solution if we have hydroxide anions. So we can look for hydroxide in our formula. We can also look at some examples that we've seen, which would include nitrogen. So we talked with our Lewis bases as well as our Bronsted-Lowry bases, that if we have nitrogens with lone pairs, they can accept hydrogens. Nitrogen has to have the lone pairs, so what we would look for is nitrogen with 3 bonds. If nitrogen has only 3 bonds, that means it has its lone pair. That lone pair can be used to accept hydrogens and donate electrons. And the other thing we've seen were negatives. So negatives, again, very often mean we've got extra electrons causing that negative charge, and they're often present in the form of lone pairs. In the case of our acids, we're going to look for hydrogens out front. That's very often where we're going to indicate that polar hydrogen that can be lost. We can have the one exception where we're not going to see the hydrogen up front is when we have our carboxylic acid. So a COOH or a CO2H. Those usually have the hydrogens listed last. So we can have hydrogens out front or a COOH. Those have got those polar hydrogens that can be donated. In the case of a Bronsted-Lowry acid, they can release and form hydronium in the case of Arrhenius acids. We could have positive charge, so that brings in our Lewis acid definition. Or we could, again, see things like our BF3 or our non-metal oxides. Now, also recall that we have amphoteric compounds. Amphoteric can be both acids and bases. To be amphoteric, they need a hydrogen they can donate, and they need negative that can accept hydrogens.